we're kind of working through how we actually get to that. So let's see what we have so far. We've determined that the velocity of B is going to have to be equal to the radius of AB times its angular velocity. Okay, do we see that? So tangential velocity at B has to equal angular velocity of AB times the radius from A to B. Okay. All right, and then we came up with the position of C from the point of view of B. So we're going 3 cosine theta I hat plus 3 sine theta j hat. Our theta is 30 degrees. And then we said that velocity of C could be written in terms of velocity of B plus the velocity of C relative to B. And so that's an angular velocity crossed with the position of C relative to B. Okay. So far, so good? All right, so what might we want to do next? Is there anything else we know here that might help us to solve? Okay, so we know the velocity at C. We know it's 4 feet per second straight down. So we do know that term. And we've defined RC with respect to B. What else do we know?
Do you know the length of the bars?
Okay, so we've got the lengths of the bars. Is there anything about, so is there anything we know about how B has to move? Is there anything that we can infer from what's there? This is really going to be a point that's important for most of what you end up doing.
You know what direction you go? Or
Yeah.
down.
So why down? Okay. Yeah, so because point B has to rotate about point A, and AB can't change lengths, the velocity of B has to be tangential to AB. So it has to be straight down. Okay, so VB is going to be straight down. Okay, so we can maybe start to put in some of the things that we know and see what we can solve for. Okay. So we have VC is negative 4 feet per second in the j hat direction. We know that has to be equal to VB plus our cross product. But we said VB is negative 2 omega AB, and we've just determined that it's negative j hat direction. Okay. Okay, and then we have our omega BC that we don't really know much about, but do we know a direction that it would have to rotate? Or at least an axis?
Doesn't rotate on, actually, I'm not sure what axis it would be, but it's in a clockwise fashion.
Okay, so it
Because
might be
one C
clockwise.
is going down.
It's going to have to be about an axis that's into or out of the page, perpendicular to the page. Yes? So if it's rotating, it's going to rotate. It's going to rotate like this or like that.
Yeah.
One of the two. So it's rotating about an axis that's either into or out of the page. So it has to be in a k-hat direction. And then we're crossing that with RC with respect to B. So that's 3 cosine 30 I hat plus 3 sine 30 J hat. Okay, so then we've got our -2 omega AB J hat. And if we do our cross product, we've got a K hat crossed with an I hat, which gives us K cross I is
Negative.
try again. Positive J. So remember we've got I hat, J hat, K hat. And so if we did I cross K, we'd get a negative J, but we did K cross I, so we get a positive J. All right, and then we've got K crossed with J. So K crossed with J. K crossed with J is
I think it's I had, or negative I had.
negative I hat. So if you don't remember, always come back to kind of this circle. So if we go from J to K, we get to I. If we go K to J, we're going backwards, and so we need a negative I. Okay. So at this point, we can treat I hat and J hat as separate and as independent of one another. So if we look at the I hat components, we have 0 I hat on the left side equal to -3 sine of 30 degrees omega BC I hat. What does this tell us?
Wait, is that a greater than sign?
Nope, that's an equals. What does that tell us? Let me zoom all the way in. I don't know why that was intended to be a useful feature. Yes, there we go. So this tells us that omega BC has to be 0 because 3 sine of 30 is 1.5. So that part's not 0, I hat's not 0, omega BC has to be 0. Good. All right, you guys are following along, very good. Okay, so then we can look at our j hat direction, and we've got -4 j hat is equal to -2 omega AB j hat plus 3 cosine 30 omega BC j hat. But we just said that one's 0. So -4 is equal to -2 omega AB. Okay. And so this is going to tell us that omega AB has to be equal to 2. Now, we have a negative sign in here because we were accounting for the direction we were going. But we have to take a look at the problem and decide whether omega AB should be positive or negative with our rotation. So if we go back and look here, if the velocity at this point is straight down, which way is AB rotating? It's rotating clockwise, which means we have positive or negative angular velocity. Has to be negative, okay? So we had accounted for VB being down, but we also have to look at what our actual angular velocity is, and it's going to be -2 radians per second, k hat. Okay. Does that make sense why we did that? Okay. So we were essentially solving for, here we were essentially solving for a magnitude of our angular velocity, since we'd already accounted for its direction. Okay, so omega BC up here, there's a question, why did we do omega BC as k hat? And that's because when we're talking about rotation and about something rotating, we look at the direction of the axis it's rotating about, not the plane it's rotating in. So if I've got x and y, and I'm rotating in the xy plane, my axis is perpendicular to that. And so it's either going to be positive k hat or negative k hat. So when we wrote this one, we didn't necessarily know whether we would rotate clockwise or counterclockwise. It turns out we're not rotating at this point. But essentially, we have to account for one of our directions so that our cross product works. So for the most part in this class, we're dealing with planar motion. So we may do some things that are a little more three-dimensional, but they'll always kind of within where something is moving, they'll be planar. So you might have a planar motion here, and then perpendicular to that, some other planar motion happening, but we won't necessarily have one object moving in 3D. So So pretty much everything will be planar to some extent. And so generally speaking, as long as that's true, we typically pick the XY plane to operate in. And so we'll always have a k-hat rotation, if that's what we're looking at. Okay, so then here we have omega AB we do have a j-hat direction associated with it, but it's because of this. So because we're really looking at VB is in the j-hat direction, but its magnitude is equal to the radius times the angular velocity. And so we're basically just subbing this in for the magnitude of VB. And so that's why there's a j-hat here. Okay, and then the other piece of this is that we know we're moving, we know we have to have VB move in a negative j-hat direction. And so here we're actually accounting for the direction of omega AB in the problem. So we could also go through and just solve this with a positive value, and then omega AB would work out the way that it needs to in terms of sign conventions. But just making sure that when you're actually, so making sure that you're kind of tying direction of rotation to what would actually be happening on the diagram. So here, the only way for B to move down is for omega AB to be clockwise. And so if it's clockwise, we have to have clockwise rotation. That's a negative direction, or negative k-hat direction. Does that make sense? Okay, so it's going to be really important to keep track of where our directions are and how we're going from one set of directions to another. So just as we keep moving through this, that's going to be key, because it's only going to get more complicated from here. All right? Okay. You ready to try another one? All right. Got one on the other side of the page. So here we've got a cylinder that's rolling without slipping on a conveyor belt that's moving at a particular speed. And we'd like to find the velocity of point A at the instant shown. So we know that the cylinder has a clockwise rotation, clockwise omega of 15 radians per second. And so that's pretty much what we know at this point.
Is that 0.5 feet just radius, or does it have like a proper failure like feet?
That's the radius.
It's just like a radius small only.
Yep, so we've got a cylinder that is rotating. Okay, so is there anything weird you noticed about this to begin with? What are you seeing?
Look at the walls.
Let's see, can you guys see that now? Sorry,
Can I take a crack?
sure.
It's your x-axis. Okay, because the z-axis is the true two-dimension.
Eh,
That's
Somewhat.
about it. What?
somewhat. So that's really not the issue.
It just doesn't look straight like that, rather.
It's kind of just offset so you can see the side of the cylinder. So
Hopefully.
perspective. We're looking at perspective here. So other than the strange drawing, what do you notice that looks a little weird here? Yeah, so we're rolling that way, but the conveyor belt's also moving that way.
So it's got super speed.
So it's, you know, it's like getting on one of those moving sidewalks at the airport, right? So you've got something that's rolling forward as the ground under it is moving forward. Okay, so just so we see that, useful to just make sure we understand what's happening in a problem before we start trying to solve it. Okay. So what should we think about doing first? Knowns and unknowns, always a good first option. So what do we know here?
Radius is 0.5 feet.
Okay. What else?
Rotational speed.
Okay, so we've got a rotational speed. Can we put that in vector form?
Probably.
Somebody want to help them out? What's our angular velocity? Okay, or put into vector, a little more into vector form? What would we say?
Yeah.
K hat, which one? So right hand roll, that's your right hand. Where is it rotating? And where is your thumb pointing when you do that? So we do this that way, and that would be negative k hat. If we do x cross y, that's out of the page for positive k hat. So this would be negative k hat. Okay. Okay. What else do we know? What else does the problem tell us?
Velocity of the conveyor belt.
Okay, so we've got the velocity of the conveyor belt. So we've got VC is 2 feet per second in the I hat direction. Is there anything else that tells us? There's some key words in the problem. Rolls without slipping. Okay. So what does it tell us if we're rolling without slipping?
Normal force and friction.
Not so relevant here. We're working with kinematics. So we're not worried about what forces are. Okay, we've got one online. So VB has to equal VC. So if we're rolling without slipping, we can't have a difference in velocity between the bottom of our cylinder and the point it's in contact with on the conveyor belt. So VB and VC have to be the same. Okay. So those are kind of key points. Then what are we trying to find? Velocity of A. Okay. And we've got our equation, V sub A equal to V sub B plus omega crossed with R. Okay, so is there something else that we need to write down before we try and solve this? What haven't we talked about yet? We need RAB? Okay, so what is our A with respect to B? In other words, where is A from B? How do you get there? Okay. In the x direction, how do we get from B to A? -1 radius. And then in the y direction, we need to go up 1 radius. Okay. Okay, so these are the pieces that we're trying to find. This is the type of a list that's going to be very helpful in solving these problems. You're going to end up with lots and lots of components as we get into more complicated scenarios. And so being able to pull the information from the diagram and write it down in these terms is going to be very helpful. Okay. All right. So we have VA equal to VB plus omega crossed with R. And so if we start putting some information in, we'll have VA and an X component in the I hat direction plus VA a Y component in the J hat direction. I'm gonna just go ahead and split those so that we've got them separated. So now that we've got them separated, we can put in the rest of this. So we know VB has to be equal to VC, so that's 2 in the I hat direction. We're adding to that omega, which is -15 K hat, and crossing that with -0.5 I hat plus 0.5 J hat. Okay. So far, so good? Okay. So we'll leave our 2 I hat alone and solve our cross product. So if we take 15, -15 times -0.5, what's that give us? Okay, so we've got a 7.5, we've got a negative cross a negative, so that gives us a positive, but then we also have to account for K cross I, which is J hat, positive or negative? Positive, okay? And negative 15 K hat crossed with 0.5 J hat. We get a negative, or sorry, we get another 7.5. We have negative from our 15. K hat cross J hat is a negative I hat, but we've got two negatives. So it's a positive I hat. Okay, do we see that? So from the numbers, we've got one negative, and from the directions, we've got another negative. So we end up with a net positive. Okay? Okay. So now we can go ahead and separate I hat and J hat. So on the I hat side, we have VA sub x. And we need everything with an I hat, so that's 2 plus 7.5. And so V A sub x is 9.5 I hat. For J hat, we have VA sub y equal to 7.5 J hat. Okay, so VA is 9.5 I hat plus 7.5 J hat, and that'll be in feet per second. But we'd also like to get magnitude and direction for this. So VA, take a square root of 9.5 squared plus 7.5 squared, and we'll get 12.1. And then a direction. And we want the y component divided by the x component. And we should come up with 38.3 degrees. Okay. Do you understand where that came from? Okay. So one other thing that we're going to look at, if we were to draw out our cylinder kind of face on, the velocity at our different points, so we've got B and A. So at B, we've got a horizontal velocity that's 2 feet per second. At A, we have a component that's forward and a component that's up. And so we end up with kind of a net VA, and it's that way. And that's using a radius here from B to A. And so it turns out that the velocity here at A should be pretty close to perpendicular to the vector from B to A. Okay. So this will be important as we keep going. Let's see. So whether or not we change it from components to magnitude and angle is going to depend on, it's really going to depend on what you're asked for. Usually it's a good idea to go to magnitude and angle if you can, but vector format or the component form is usually valid too. Just make sure you're following what is actually asked for. Okay. So one of the things that will be important to watch with something like this is that we've got an object that isn't actually rotating about its center of mass. It's rotating about a different point. Okay, so when we've got something that's rolling, usually we're going to rotate about the point that's in contact with the ground. And it'll depend on what our ground is, what keeps us needing to rotate about a certain point. Okay. Are there questions at this point? Okay. We have a question? We want to clarify? Okay. All right. Okay, so we will take a look at our next set of items. So we're going to be looking at the instantaneous center of rotation. So the instantaneous center of rotation is also known as the center of zero velocity. And so similar to the last problem, we're going to be looking at a cylinder that's kind of rolling along the ground. And so at the point where the cylinder is in contact with the ground, so right there, its velocity must be 0. If it doesn't slip. Okay, so this is like your car tires. If it is a nice sunny day out and you're not doing anything too crazy, the velocity at the point where your tires are in contact with the ground should be 0. If it's not 0, that's called skidding, right? Or hydroplaning, or whatever else may happen, ice. If the point where your wheel or where your tire is in contact with the ground doesn't have a velocity of 0, you do not have much in the way of traction. Okay? So we're looking at what we call the instantaneous center, and we'll abbreviate that IC. And so if the cylinder is rolling forward, and we've got a couple of different points that we're monitoring and looking at, we can kind of see how things are rolling as we roll along. So it's called the instantaneous center of rotation because if we look at just this point, as we keep rolling forward, C will eventually become the instantaneous center of rotation, and then B will become the instantaneous center of rotation. And so it's just for that instant that the velocity is 0 at that point. Now, if we only have velocity 0 for a really short amount of time, what does our acceleration look like? Will it be 0 when we're stopped? Or when that point is stopped?
Yeah, sure.
So it can't be. We can't have 0 acceleration if we're only going to be at 0 velocity for a really short instant in time. Okay. So acceleration won't be 0, but velocity will be just instantaneously. Okay, so if we look at this on a little bigger space, a little bigger cylinder, we've got our instantaneous center. And then we've got the middle of the circle, point B and point C, which I apparently moved down a little bit from what you had it in the higher diagram. Okay, so on here, we're looking at a number of different pieces. So if we just look at the radius of the cylinder here, we go from the instantaneous center to the middle, to the axle of the wheel. We have a radius O with respect to IC. And so it gives us a velocity straight forward. Okay. If we look at B, we have a radius B with respect to IC. And its velocity will actually be this way. And for C, and we actually get a velocity down that way. What do you notice about all of these? So our velocities and our radii are perpendicular because when we have a rotation, we always have velocity in a tangential direction. So here, because we're rotating not about the center of the wheel, but about the point that's in contact with the ground, we have to use the radius from the point that's in contact with the ground from our instantaneous center to that point to determine what way our velocity is going. Okay, so this is going to be true if we're rotating this way. So our omega is going to cause rolling toward the right side of the page. If we were rolling the opposite way, what would our velocities look like?
Because it's in the opposite direction.
Yeah, so they just kind of be flipped around to the opposite direction. So if we were rotating That way we'd have the same line, but our velocities would be in the opposite direction. Okay. Okay. So as we're rotating, velocity of a given point is always going to be perpendicular to the radius from the instantaneous center of rotation to that point. Okay. So since our rotation is about our instantaneous center, the vector from the instantaneous center to all other points will be perpendicular to the point's velocity. Just as if it were rotating about its center of mass, with velocity perpendicular to the radius. Okay, so if we have a wheel or a gear that's not in contact with the ground, it's just rotating about the center, our velocity of every point is perpendicular to the radius. When we move that center of rotation somewhere else, our velocities are perpendicular to the radius from that center of rotation to the point that we're looking at. Okay? And so we can say that the velocity of a point is equal to the angular velocity times the radius to that point from whatever our instantaneous center is for any point. Okay, and then we've got a couple of points at the bottom. Like I said before, just because our velocity is 0 at our instantaneous center does not mean that our acceleration is 0. Our acceleration will almost always not be 0 at the instantaneous center of rotation. The other piece is that if we've got a rolling cylinder, our instantaneous center is on the body. But for other types of systems, the instantaneous center may not be on the object we're interested in. It may be outside of that. We might be rotating about a different point. Okay, questions at this point?
Since it's usually not 0, but we have to work with like questions where it is.
I will not rule it out.
What?
I will not rule it out,
Oh.
but it is unlikely.
If it was still working.
Yeah, so it depends a little bit on depends on the system. So it could be a system where you have something something rotating about a point that's not actually on the object that's rotating, and so then it might not have an acceleration to it. So it depends on the system. Okay, so your next big question should be what? We're interested in finding an instantaneous center of rotation. So the next question should be, how do we figure out what we're rotating about? So So how do we figure out, if we have a rolling cylinder, it's pretty obvious. But if we look back at this problem, how do we find our instantaneous center of rotation? What do we think? So for AB, it's pretty obvious, right? We have to rotate about the pin. What's less obvious is how the rest of the system would be rotating. So we've got a number of scenarios that will help us kind of think through how we can come up with an instantaneous center of rotation. There's a really big sigh from somebody. Okay, so this looks intimidating. It's not quite as bad as it looks. So for our first scenario, if we know the velocity of point A, so it doesn't matter where it is, but if we know what our velocity of a particular point on an object is, and we know the angular velocity, so we know what omega is, we can essentially find where our instantaneous center is by drawing a line perpendicular to our velocity. That's what this line here is. And then figuring out both which direction that vector has to go to get us to the correct direction of rotation. So if I put my instantaneous center of rotation over here, and VA is going that way, does that match the direction I drew omega? No, it's the wrong way. So we have to be on this side of it somewhere. Okay? So then we're just looking for an RA with respect to IC that gives us the correct magnitudes, or the correct relationship between angular and velocity of the point. Okay, so we're drawing a vector that is perpendicular to VA with a magnitude, let's see, that's equal to VA divided by omega, and a sense or a direction that allows VA to cause omega. Okay. So our IC will be here. Okay, so I'll say that again. If we know the angular velocity of an object, and we know the velocity of one point on that object, we can draw a line perpendicular to that velocity with a magnitude or a length that gives us the right relationship between V and omega. And then the sense means which direction are we going. So we said we couldn't put our IC over here because that would cause rotation the wrong way. So it has to be over here. And so that's how we we know those two things, that's how we figure out what point we're rotating at. Trying to decide if I have lost you all. Okay? All right. Got at least one with me. Okay.
So what are we trying to look for in that scenario specifically? Like what info do we need so we can distinguish?
So for this one, we're saying for all of these, we're going to try and figure out where our instantaneous center of rotation is. So where is the instantaneous center of rotation? For this one, we know the velocity of A, and we know the angular velocity of the whole body. Okay? And so we're going to use that to figure out where we're rotating about. We know velocity has to be tangential to the radius, which means we have to have a radius that's perpendicular to our velocity. And it has to be the correct direction to give us rotation in the right direction. Okay. And we also know that our velocity has to be equal to omega times r, which is where we got the magnitude of r equal to v divided by omega. Okay. So the other scenarios are all knowing two different velocities, or velocities of two different points on our object. Okay? And just different ways of looking at them. So if we know the line of action of two non-parallel velocities, VA and VB, at points A and B, we can draw lines that are perpendicular to each of them, or each velocity, and the instantaneous center will be at the point where they intersect. Okay, so here if we know maybe VA is that direction and VB is straight down, then we essentially take a line perpendicular to each of those lines of action and look for where they intersect. And wherever they intersect is where we have our IC. Okay, so once we've figured that out, we can figure out where that point is in space. But we're really just trying to initially figure out what are our perpendicular directions and where do they intersect. So we functionally end up with an R A with respect to IC and an RB with respect to IC. But we're not necessarily looking for a magnitude at first. We're just looking for what's the line of action of the velocity, and then drawing a line perpendicular to that for both points and looking for where they intersect. Okay. Okay, so far so good? Yep,
So there's no angular velocity present? in this?
there is angular velocity present, we just don't know what it is.
Oh,
So instead of knowing VA and omega, so here we knew this one and we knew that one. Here we know this and we know that.
yeah, that's what I mean, I didn't mean like it doesn't
Yeah.
exist.
Yeah,
I was just saying what we were given.
right. So we weren't given any information about our angular velocity here.
Just
Just velocity or directions of velocities of 2 points. Okay. And the key here is that these are non-parallel velocities. Okay. Because you might have guessed what our next one is going to be.
parallel.
We know 2 parallel velocities. So if we know the magnitude and direction of 2 parallel velocities, and this will be again VA and VB, we can use similar triangles to find our instantaneous center. Okay. So we're going to draw 2 lines. One is going to go one line will go through points A and B perpendicular to the velocities. And then the second is going to connect the tips of our velocity vectors. So we need to have our vectors drawn to scale. Okay. So what this might look like, we've got a point A and a point B, and we have one velocity that direction, and a second velocity this direction. We draw our first line through A and B perpendicular to the velocities. And we draw our second line from the tip of one velocity vector to the tip of the other velocity vector. And the point where those 2 lines cross is our instantaneous center. Okay. The other possibility would be something like this. So if we've got VA and VB, we draw the line that connects through them perpendicular to the velocities, and then the line that connects the tip of the vector to the tip of the vector, and keep going through. And our instantaneous center is again where they intersect. Okay. How are we feeling about this one? These all kind of make sense?
Oh, wait, hold up, I'm not done.
Okay. I'll leave it there for a couple minutes. before I continue.
Oh, I missed something too.
Okay. Okay. Getting close?
Yeah.
All right. That was a maybe. Any questions on this?
Doesn't matter the quantity of velocity, like VA can be 2 meters per second and VB can be either less than or greater. Would that affect where the IC is?
Oh, yeah. So so that's why we want to draw these to scale. So if VA is 2 meters a second, and we're drawing VB this way, VB should be bigger than VA. If it's not, if it's less than VA, we'd have to have, so just alternative version here. If VA is here and VB is where it is, you'd have a line that got drawn like that, and your instantaneous center would be down here. Does that make sense? So we're looking for where do the velocities match up so that they're definitely rotating about the same point. So where that point is important in terms of solving for things and understanding how an object is moving. But we'll find that based on whatever velocities we have to work with. Okay, so let's try something a little more fun. Okay, so last time we had one conveyor belt. Now we have two plates that are moving and a cylinder rolling in between them. They have different speeds and different directions. And so we'll have to figure out how this is rotating based on that information.
There's still no slipping.
And there's still no slipping. Okay, so we have speeds and directions for the two plates. We're told that there's no slipping. And so we need to figure out what the velocity of the center of the cylinder C is and the point we're rotating about. Or, let's see, the point we're rotating about is kind of in there, but angular velocity is what we want. Okay, so what do we know?
Velocities for the conveyor belts, VD and VE.
Okay, so we know the D and VE. More importantly, as we're trying to figure out the angular velocity, what points do we know speeds of based on what we're told? How is there not slipping if the velocities of the plates are different? It's not rotating about the center. Okay, you said. Okay, so velocity of A is going to have to be equal to VE, and so that's 0.25 meters per second And we'll call that the I hat direction. What else do we know?
BB is equal to BB.
Okay, so that would be, how would I write that down? Okay. Okay, so because we don't have slipping between the cylinder and the plates, we know what the velocities of those 2 points have to be. So are we rotating about the middle? Are we rotating about point C?
Not exactly.
We can't be, right?
No.
Because if this whole body has one angular velocity, the radius from C to B and C to A is the same, but we get different tangential velocities. So we have to have some other point that we're rotating about. Okay? Okay. All right, so we'll just go ahead and write that down quickly. So R B with respect to C as a magnitude is equal to R A with respect to C, but VA is not equal to VB, which tells us that C is not our instantaneous center of rotation. Okay. Okay, so we do have, we'll have a diameter that's equal to 2 times the radius. That'll be 0.25 meters as our diameter. And so if we kind of redraw our situation here, we have VA at the top, that's 0.25 meters in the positive I hat direction. VB at the bottom is 0.4 in the negative I hat direction. We know that the distance from A to B is 0.25 meters. Okay, and so we've got A and B. Which scenario is this? So we have 2 parallel velocities, so it's our third scenario from the previous page. So what do we need to draw?
Line from one velocity to the other.
Okay, so we're going to draw a line through both velocities. So from one velocity to the other, which way are we drawing it? Okay, so we need perpendicular. We need a perpendicular line through both points. What else do we need?
Okay, line connecting the velocities intersecting with the line we just drew.
Okay, so we need to draw a line from the tip of one velocity to the tip of the other velocity. So one vector to the other. And so that's where we'll find our IC. Okay, and we're going to call this some value y, or some height y. Okay, So how did we say we find where the IC is with this? Did you have a question before we go further?
Oh, there's one other sort of another question.
Okay.
It's not really, that's what you said.
So similar triangles. Okay. So if we do that, we're going to have an R here and a different R here. So RB and RA. And so we can say VB needs to be equal to the angular velocity times that unknown distance. VA will have to be also has the same omega value, but what's its radius?
0.25 meters minus 1.
Okay, so 0.25 meters minus y. Okay, so we have two equations. How many unknowns do we have? Two. We don't know omega and we don't know y. But we know VA and we know VB. Okay? So we can solve it. Okay, so VB has a magnitude of 0.4, and that's equal to omega times y. And so if we solve for omega, we get 0.4 divided by y. We can substitute that into our other equation. And so VA is 0.25, and that's omega times a distance. So we can substitute 0.4 divided by y in. Okay. And we get 0.25 equal to 1 over y times 0.1 minus 0.4. Okay, because here our y's cancel. All right, and so if we move the 0.4 to the other side of the equation, we get 0.65 equal to 0.1 divided by y. And so y will be 0.1 divided by 0.65. And that'll be 0.154 meters. Okay, so which radius is this again? We solved it with the VA value, but y is RB. Okay. Good. So this would be RB with respect to IC. So there's a question about positives and negatives. Here we're just worried about, we're using similar triangles, so we're not concerned about whether we've got positive direction or negative direction for any of this. So we've just got a similar triangle here, and that has to be similar to this triangle here. So we're really just working with magnitudes at this point. So that's why we didn't swap things around, positive and negative. Okay, so now if we take this y value and substitute back in over here, we have omega equal to 0.4 divided by our newfound y of 0.154. And so we'll have omega equal to 2.597 radians per second, or omega is 2.6 radians per second. Okay. Is that all we needed to find, or was there one more piece?
Velocity of the center.
So we want to find the velocity of the center. Okay, so how do we find the velocity of point C?
You can make another triangle. Because it'll be lower than the
Okay, I got part of that. But not all of it.
You make another like similar triangle.
So could we do another similar triangle? Okay. So here's what we know at this point. We know that our instantaneous center is 1.54 from B, so it's somewhere up here. And we know what our angular velocity is. So this has to be clockwise based on the directions that our values are. So we know omega is 2.6 radians per second. So what we need is this R value here from our instantaneous center to point C. So we are doing another triangle effectively. So we'll have RC with respect to IC equal to y minus the radius of the circle. So that's 0.154 minus 0.125, or 0.029 meters. Okay, and then VC is a tangential velocity. So it's omega times RC with respect to IC. Okay. So that's 2.6 radians per second times our 0.029 meters. And so the velocity of the center of our cylinder will be 0.0754 meters per second. Sorry. So that's a speed. Which direction will the center point C be moving? It has to go that way. We're below the instantaneous center. Okay, so VC has to be that way. So it has to be moving in the same direction as point B. It's actually a negative I hat direction, because we're going below where our instantaneous center is.
Could you also write it as positive I hat?
It would have to be negative I hat, right? So it depends on how we define X and Y. If we define if we defined, well, yeah, so if this is our positive I hat, this velocity has to be negative. But if we define it the other way, it'd be positive, so. Okay, questions on how we did this? Okay, so we said we knew what our two velocities of points were because those points had to move at the same speed and in the same direction as our plates. So our instantaneous center had to be between them. And we could find that location with similar triangles. If we had drawn these all to scale, we could just measure it. But we can also solve it by saying that our velocities have to be equal to omega times the radius, and we're just worried about magnitudes here, not directions. And so then we had two variables and two unknowns. Sorry, two equations and two unknowns. We could solve for omega and for the location of the instantaneous center, and then use that to use some geometry and our angular velocity to find the velocity of the center of the cylinder. Is there another question? There was a question, I saw a hand.
Oh, I have that here.
Okay.
So, see a scenario like this, but both velocities are given, and C would be the instantaneous center.
Yep, so if our two plates had the same speed, so if they were both 0.4 meters a second in opposite directions, then the center C would have to be the instantaneous center.
And would it be true that whichever the instantaneous velocity will be farthest away from the equator, or instantaneous center will be furthest away from the equator velocity?
Yes. So so if where we've got two different speeds, whichever one is bigger has to have a longer radius. So if the angular velocity of the whole body is the same, the radius from a point to the instantaneous center will be proportional to its speed. Yep, good observations. Okay, that is what we've got for today.